Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly webinar series. Today's topic is Effect of Different Voltage Waveforms on Partial Discharge Results on Medium Voltage Cables. My name is Jamie Smith, and I'm the Digital Marketing Specialist for Megger North America, and I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. Okay, on the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NETA CTD and one PDH or 0.1 CEU just for attending today. You will receive this in an email within about 2 business days after the webinar. And that email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Jason Sushak, Megger Applications Engineer. Also, to assist with the question and answer session, we will have a panelist joining us by the name of Robert Prost, and he's another Megger application engineer. Okay, let's go ahead and get started. Thank you for joining us today, Jason.
Thank you, Jamie. The format for today's webinar is, of course, on the medium voltage cables for partial discharge testing. And the topics we'll go through are a brief introduction. We'll talk about the different VLF waveforms that are part of this study. We have a case study to show you, and then we'll go through interpreting the results of the case study. So a pretty straightforward webinar for you today. So we'll get started now with the introduction. So a little bit ago, we did a webinar, I guess a couple months ago, on partial discharge testing. There's a lot more in-depth information on that, for more in-depth in the topic, but we'll have a brief review right now. So partial discharge testing is a state-of-the-art technique for testing cables, especially medium voltage and higher voltage cables. It's a very powerful test, gives us a lot of useful data. And what we can do with partial discharge testing is identify weak spots in cables, and especially in cable accessories, before they break down in service as part of a maintenance test program, or before the cable's even energized, so as part of an acceptance testing program. In an ideal world, we would perform these tests under 50, 60 hertz. That's what the cable sees in service. That's what we'd like to see. But the equipment to do that is very large, very heavy, and very expensive. It requires a lot of power to do this testing. So because of that, most commonly, cables are tested using VLF or very low frequency technologies. So we have a couple of different options when it comes to VLF waveform. And what we're here today is to discuss if the waveform we choose will make a difference in the partial discharge results. So what is partial discharge? You may be familiar with corona discharge in air, where sharp points or anything on overhead lines will kind of emit this bluish glow. It's a very similar phenomenon to partial discharge, except, of course, we can't see into the cables, but it looks very similar. What's happening is it's ionizing the insulation material, but it's not actually causing a full breakdown between 2 conductors. So it's just a small part of the insulation that's actually breaking down. The amount of partial discharge depends on the electrical field, and what we're looking for is a voltage difference between very, very small areas of the insulation, small voids or small defects in the insulation. And that's exactly where partial discharge occurs, in small voids, small defects. In the insulation, the bulk insulation of the cable, it can occur there as defects from the manufacturing process, but it's very uncommon to see that. If there's any kind of contaminants or impurities get into the insulation material, or if we wind up with voids for whatever reason, or as part of the installation process, if we exceed the bending radius of the cable, all these things can contribute to partial discharge in the bulk insulation of the cable itself. What we see much more commonly, though, is partial discharge in cable accessories, splices and terminations, places where people have put their hands on it. Even the best trained technician can make a mistake, and that's what we're here to find out, to try to avoid those before they go in service. And partial discharge can also occur just through aging processes as well. Nobody has to make a mistake. It can just be a normal aging process. But it comes from, improper cutback distances. If you're used to one kind of splice and you make a different one and the cutback distances are just a 1/4 inch difference, that could be a cause of partial discharge. Nicks and cuts in the installation as part of the installation process. Missing components, misaligned accessories, and I do have pictures of these on the next slide. What we see here on this slide is incomplete shrinking, where this whole area, if I can highlight it with the pen, that's all experiencing partial discharge because there's an air gap up here. That wasn't completely shrunk. It's very common for the top of a heat shrink splice to be, well treated, but the bottom is maybe a little bit harder to get to, and it might not be completely shrunk. So what does partial discharge look like? In the top left corner, we have an example of partial discharge in a paper insulated conductor, where this electrical tree is growing and growing, goes for a very long period of time. In the lower left corner, we're seeing partial discharge coming off of the semiconductive area of the cable. In the lower right corner, what we see is where somebody went to peel the semicon off, and their tool was set a little bit too deep and wound up scoring or scratching the insulation underneath. And all of these stripes going through the cable are places where that tool scraped the insulation, and they're all experiencing partial discharge. And finally, in the top right, we have an example of a misaligned splice where you can see that the crimp body of the splice was outside of the black Faraday cage of the splice body, and that caused, of course, partial discharge. And as you see in the picture here, that's how the splice was found, with that crimp outside of the middle of the splice. So on the next slide here, I have a video I'd like to show you. This is an example of electrical tree growth. In this video, the insulation is 10 millimeters, and there's 5 millimeters between the needles, and they applied 22 kV. It is important to note that this is in acrylic glass and not in cable insulation, so it's a little bit different, but it is representative of what cables will see in service. If this video would play, there we go. So what we'll see is on the bottom you have minutes, seconds, and frames. So we're already up to about 2 minutes of electrical tree growth. This does take a little bit for the trees to grow, and in this video it's the bottom one that fails, so keep your eye on that. And what you'll see is that the trees start growing and growing, and at some point the bottom one especially will just kind of accelerate to a very quick failure. So it's starting to accelerate now and fails very quickly after that point. So you'll see a little replay here where they show the failure, the moment of failure again. So to go through 10 millimeters of acrylic glass, it took about 11 minutes. So this partial discharge process takes a little bit of time. So keep that in mind when you're doing your VLF testing. You have to apply the voltage for enough time for the insulation to fail. I'll let the video finish here. So what we see is that if there is partial discharge present on your cables, it's continuously damaging. It causes a continued accelerating aging of the cable or joint. And eventually it creates a conductive path between the conductor and shield due to treeing, carbonization, and tracking effects. Important to note is that it continues to cause damage. Partial discharge, if it's present, does not heal itself. It only gets worse. The mode that it damages the insulation is various effects from partial discharge, such as high energy electrons and ions getting emitted from the breakdowns, UV light attacking the insulation, ozone is emitted during the breakdowns, high pressure, high temperature gases getting freed up. All of these induce cracking, induce carbonization on the channel walls, just continuously damaging process. So where does partial discharge testing fit into the overall scheme of testing? So we have here an example of workmanship issues and determinations, some distributed water trees, they're non-critical, some insulation, some workmanship issues in a splice, and finally a critical size water tree. For all of the local issues, we can use a VLF withstand test to find those as well. And for the distributed global issues, we use our tan delta testing. But what we find is that partial discharge is extremely good at locating problems in terminations and splices as well. So that's where partial discharge fits in the grand scheme of things, especially suited for splices and terminations. So what can partial discharge detect? It can detect local weak spots in the insulation, voids and air gaps. It can detect electrical trees, but only if the tree is present during testing. It's very unlikely that the tree is present during testing. We can look for workmanship issues in the splices and terminations, such as incomplete shrinking, misaligned accessories, things like that. There is some information given in IEEE 400.3, but there's no real standard available for partial discharge testing in the IEEE world. There's some more information. There's been a lot of work done in the IEC world. It's been well known for many years there, and they have a little bit more information in the IEC standards. How do we actually run the test? We might run the test by applying increasing voltage steps, for example, half rated voltage, 0.8 times rated voltage, working our way up to 1.7 or twice rated voltage, going up to 2 times rated for new cables. This allows us to find the PD IV or the PD inception voltage, which is the voltage at which partial discharge begins. How high do we have to bring voltage to start seeing PD? We run the test for a period of time to create a map. After we find that, this can take anywhere from a few seconds to an hour. Cables in worse condition tend to be a little bit easier to map. And then we can end with a monitored withstand if we choose to, interpret the results and print the report. Just some definitions, and we will circle back to this slide in a minute, but I want to get some definitions out there in front of you as we go through this. So some important terms: continuous versus non-continuous testing. Continuous tests are a voltage source that's applied continuously, periodically, something like a sine wave. Non-continuous is a voltage that's applied in discrete pulses, as you'll see, like our damped AC. Offline versus online. Offline testing requires a separate power source, and it usually requires you take a planned outage. Online testing, you may need an outage to install some equipment, but once the equipment's in there, you can measure PD periodically. And we'll talk about that in a minute as well. PD inception voltage, that's the voltage that we have to raise, come up to start seeing partial discharge. The PD extinction voltage, once we start seeing partial discharge, how low do we have to bring our voltage to stop seeing PD? We'll look for a PD pattern, that's the map that I was talking about, and we'll have an example of that in a minute. The PD level, or the intensity in picocoulombs, and the PD count, how many events do we see? So, online PD, VLF or damped AC technology is used to do offline PD testing, but there are some online technologies as well. The online PD allows for the user to perform a PD test without taking an outage, although many of the online tests do require you to take a planned outage to install equipment and possibly to remove equipment when it's completed. The limitation of online PD is that it only allows for PD testing at system voltage. You know, no matter how good of a friend you are with the system operator, if you call them up and say, hey, can you give me 1.5 times voltage, they're just going to laugh at you. They're not going to help you with that. So it only allows us to do testing at rated voltage. We're not able to find the PD IV. We're not able to ramp the voltage up to find the inception voltage. The other limitation with online PD testing is that it only tells us if PD is present at the time of testing. It's kind of like taking a picture. There's no way for us to tell what happens next. There's no way for us to tell if this cable is in very good shape or just barely passed the test. Online PD, though, is useful as an alarm. If it's continuously monitored, it'll say, hey, I'm starting to see partial discharge at rated voltage. We should take some action. And you can also use it as a screening method for offline PD measurements. Offline PD is what we'll talk about today. for the most part, all of the waveforms that I'll present in a minute are offline PD testing. It solves a lot of the deficiencies from online PD, but it does require taking a planned outage each time you want to do the test. Offline PD allows for diagnostic testing, which allows us to predict some future reliability. We bring our own power source, so we're not going to ask the system operators to raise the voltage. We can apply the voltage that we want to. This allows us to get some diagnostic results, and we can determine the inception voltage and the extinction voltage. Because we bring our own equipment, we can design it as PD-free as possible, so we tend to have a lower background noise as well to enable more sensitive PD testing. So that's the brief introduction. I'll talk about the voltage waveforms that we have available to us. So it's important to keep in mind that partial discharge is a frequency-dependent phenomenon. It depends on the rate of rise of voltage, or the dV/dt, especially at the point of zero crossing. Cables operate at 50 or 60 hertz power frequency. It would be ideal to do our testing at that same frequency. But as I pointed out, this requires very large, very heavy, expensive test equipment. Because of that, most often cables are tested with some VLF or damped AC technology, which requires about 600 times less power, which means we can make much, much smaller, much more portable, much more affordable testing equipment. And there are certain VLF technologies that enable power frequency-like testing that gets a very similar dV/dt to partial discharge. So what effect does the voltage technology that we choose to use, what effect will that have on our PD results? So to characterize the waves, power frequency at 50 or 60 hertz, at 50 hertz it has a 10 millisecond, and at 60 hertz it has an 8.3 millisecond duration of polarity reversal. That's the time it takes to go from a positive peak to a negative peak. The VLF cosine rectangular or damped AC, they operate in the range of 30 to 500 hertz, which corresponds to 16 down to 1 millisecond for duration of polarity reversal, or within about 1 order of magnitude of power frequency. And the frequency that these two technologies operate at is dependent on the length of the cable. VLF sinusoidal operates at 0.1 hertz, which means that it takes 10 seconds to perform 1 cycle, or 5 seconds to perform half a cycle. So it takes it five full seconds to go from fully positive to fully negative, or 5,000 milliseconds. This is in the range of about 2 orders of magnitude off of power frequency. So to give a little bit of a schematic overview of what these look like, I have some power frequency cycles in blue there as a reference. I have 1 shot of damped AC in the red, 1 polarity reversal of VLF cosine rectangular, and a portion of a VLF sine wave on there. So what you can see is the damped AC. The reason I have this slide up here is so you can see that the damped AC damps out very quickly. The voltage goes from full to 0 in just a few cycles. So if I zoom in a little bit closer here, what is important to note, my laser pointer here, we can see that the damped AC and the the damped AC and the cosine rectangular, they transition from in this case a negative peak to a positive peak at about the same rate as power frequency, where the VLF sine in this case looks almost flat, especially when we zoom into this zoomed in view here. And just so you guys don't accuse me of lying to you, it is important to note that this is an idealized condition. I have these cosine rectangular and damped AC represented as exactly 60 hertz. It's very unlikely you'll ever see that. But the idea is to illustrate the point that they're in the same frequency range as power frequency. Again, I said that both of these technologies operate in the 30 to 500 hertz range, and that is in the power frequency type of range. So how do we create these voltage wave shapes? The VLF sine technology, it requires 2 power supplies, a positive and a negative, and it also requires discharge resistors. Obviously, we use the power supply to charge the voltage up to a peak, and then we use the resistors to discharge from a voltage peak down to a 0. So we're converting that stored electrical energy in the cable to heat every time we discharge the cable. we have exactly 2.5 seconds to bring the cable from 0 voltage to maximum, and exactly 2.5 seconds to go from maximum back to 0 to discharge that. So depending on the power that we have available in our power supplies, we have limits to our testable length. How much capacitance can I charge in 2.5 seconds? The other thing to keep in mind with these discharge resistors, they create a lot of heat, so that imposes a testable limit as well. With the cosine rectangular and damped AC, we utilize a resonance circuit. So you can see in the diagram here that we still have 2 power supplies, a positive and a negative, but we have a switch here, and we use the resistance and inductance in the unit and the capacitance of the cable, and if necessary, a support capacitor to create a resonance circuit. With the cosine rectangular, we close the switch, charge the cable up, and hold it for 5 seconds. 5-second DC hold. At the end of that 5 seconds, if we want to, we can measure leakage current. When we switch from a negative to a positive, we close the switch, S here, and change our power supply. There's a blocking diode in there to ensure that we only resonate for half a cycle, and then we hold polarity in the opposite sign, and so on and so forth. There's no bleeding resistors on here. There's no discharge resistors in this circuit. We actually recover a lot of the energy. It's very similar for the damped AC, except instead of using a blocking diode, when it's time to close the switch, we just let it decay out naturally through the resistance in the circuit. So if we compare these waveforms then, what you can see is that there's a little bit of a breakdown here in various categories. I'll try to pull my laser pointer up here. So continuous testing, 60 hertz, cosine rectangular, and sinusoidal are all continuous. They're a periodic waveform, and they continue until you stop. Damped AC is a one-shot, and then there might be some time between the next one. So it's not considered a continuous test. We have a comparison of the transition times. As I pointed out, our baseline is 8.3 milliseconds. Cosine rectangular is in the range of 16 to 1, same with damped AC, and sinusoidal is in the range of 5,000 milliseconds. Cosine rectangular and damped AC have very high testable capacities because of that resonance circuit that we set up, while VLF sine has a more modest testable capacity because of the discharge resistors and the need to charge it up every time. When we're talking about PD testing, our test time, we can do a very quick test with 60 hertz and damped AC because they oscillate very quickly. With cosine rectangular and with sine, we only get information once every 5 seconds. So we can only do our measurement once every 5 seconds. It takes a little bit longer to do those. We can do withstand testing with all of these waveforms, although damped AC is defined withstand testing in IEEE 400.4. It's done a little bit differently than with these continuous waveforms. And when we talk about what these waveforms are best suited for, 60 hertz is great. It's good for partial discharge and withstand testing, but it is high power requirements, big heavy equipment. Cosine rectangular is great for withstand testing or partial discharge monitored withstand testing. Damped AC is great for partial discharge diagnostics, so a very quick and very gentle test on your cable. And 0.1 hertz sine, it can be used for partial discharge, but it's well suited for tan delta and for withstand testing as well. So we'll talk about our case study here. Like I said, we'll circle back to these important terms. I described some of these already, but the most important one that we have to talk about is our inception voltage. This is one of the most important pieces of information that we get from a diagnostic test. So as I said, what voltage does partial discharge start, and at what voltage does it stop? We have to relate these to above and below system voltage. So if my partial discharge inception and extinction voltage, as we show here, are both well above operating voltage, that's a condition I can live with. This cable's not seeing partial discharge in its day-to-day life. It might be, depending on where these fall exactly, I might be more concerned and come back and do testing more frequently, but I can live with this. On the flip side is if my inception voltage and extinction voltage fall well below system voltage, this is a very bad condition to be in, because no matter what, this cable is always seeing partial discharge. It's always getting worse. We need to take some corrective action if we find this condition. And finally, the third possibility is this maybe condition. This is a dangerous condition as well, where the partial discharge inception voltage is above system voltage, but the extinction is below system voltage. So what this means is that if you put that cable in service, it may not see partial discharge. But if there's a lightning strike, for instance, or a switching transient, that may be enough voltage to initiate partial discharge for just a few milliseconds. It doesn't take much. And then that cable starts seeing partial discharge in service. The only time it'll ever stop seeing PD is if it fails or if it's taken out of service. So very dangerous condition as well here. So I have a brief example here. We have, for instance, the partial discharge inception voltage. I start raising voltage up. And at the point that I start seeing PD, that's my partial discharge inception voltage. The next important number to find is the extinction voltage. And that's shown here. This would be the last partial discharge that we measure in the shot, or as the voltage decays, the last partial discharge that's measured. You might see some other signatures out there, but those were noise in this case. That's the partial discharge is the extinction, the stop of PD. The next one is the PD pattern. So we can start seeing in this case exactly where these partial discharges are occurring. So we have this one. I just picked out a couple at 460 meters, at 600 meters, and 734 meters. You can see a couple other ones on the chart as well. But these are the points that are of concern to us that we'll have to go and address in one way or another. We also take a look at the PD intensity, or the value of picocoulombs that we measure. So this one's a little bit higher than this one, and that's higher than even this one over here. These aren't the most critical factors in making a determination on how good or bad a splice is, but they are factors that we have to consider. So just the fact that this last one over here has the highest partial discharge value recorded doesn't necessarily mean it's the worst condition, but it is another factor we have to consider. And finally, the other piece of information that we have is the PD count, or the number of events that we have. So very similarly, even though this one here has clearly the highest number of counts of the ones we're looking for, that may not be the worst partial discharge out there, but it does factor into our decision making. So moving on to our case study now, we have this cable here, and we did, in this order, we did damped AC, sinusoidal, and cosine rectangular testing, all on the same piece of cable on the same day, all within about an hour of each other. So it's a very representative sample. The following slides show the results at rated voltage and at 1.7 times rated voltage. Why these two values? These two are very critical voltages. We want to make sure that there's no PD at rated voltage, and we want to see the record at the maximum applied voltage. So there are tests, there are measurements done at different voltages on here, but these are the two that I picked for this presentation. And you might be wondering where this 1.7 times comes from. Well, there is a fault condition that if you lose one phase, the two remaining phases will see 1.7 times over voltage. So we want to make sure that if this condition does occur in your system, that the cables are at least able to hold this voltage. So here's the results of the damped AC testing at rated voltage. And what we see is two areas of concern. And I should mention here, I'm only showing the A phase results just to keep it simple. But at the end of this, I do have a summary with all three phases, and the results are pretty similar across all three phases. What we show here, we have a splice here at about 750 meters that's showing 1100 picocoulombs, and a splice at 900 meters with 700 picocoulombs. And this is at rated voltage, so this is a cause for concern. We're seeing partial discharge at rated voltage. This cable's experiencing PD in its day-to-day service, cause for concern. When we bring the damped AC up to 1.7 times rated voltage, the intensity is flipped. Now the splice at 900 meters has a higher intensity of 2250 picocoulombs compared to the 1500 of the splice at 750 meters. both of these splices are cause for concern, and we need to take some corrective action on both of these splices. When we go to our VLF sinusoidal results, though, our results at rated voltage, we show no PD measured. Let that sink in for a second. There was no PD measured, even though the damped AC clearly showed two problem points. So what this is telling me is that my VLF sign is giving me a false good result, which is very dangerous as well. I don't know that there's a problem out in my system. Even when I bring the VLF sign up to 1.7 times voltage, it completely missed this splice at 750 meters. It's not shown up. And the splice at 900 meters, it shows at only 250 picocoulombs. I do have some guidelines in the end, but that 250, that's right on the edge of what we would consider tolerable for this kind of testing. So that might give you a false sense of security and say, okay, that splice isn't so bad and it only shows up at a very high voltage. I might leave this cable, this splice in service and not take action. But when we look at the results from damped AC or cosine rectangular, we say, oh no, these are very critical splices. So here's my results from the VLF cosine rectangular. In this case, it found the splice at 750 meters. At rated voltage, it did not find the splice at 900 meters, but it did find a problem in the cable insulation. That's very rare to find that kind of problem if you're testing extruded cables, XLPE or EPR. It's very rare to find a problem in the bulk insulation. But in this case, this problem was on some paper lead cable, and that's considerably more common. And this level of 500 picocoulombs is not really a cause for concern right now. And I do have some guidelines coming up in a couple of slides, and you'll see. When we brought the voltage up to 1.7 times rated voltage with the cosine rectangular, now it's able to find that splice at 900 meters, clearly finds that splice, still finds a splice at 750 meters, and this problem in the insulation still shows 500 picocoulombs. It didn't get worse with increased voltage. So you might notice that the values with cosine rectangular are a little bit higher. So we saw 4,000 picocoulombs here. With damped AC, it was 2,250. That's pretty much expected because with that 5-second DC hold, you kind of pre-charge those defects. And when it comes time to flip polarities, they have a lot more energy stored up and give us a much higher signal. So here's the summary of these results. And the first thing you can look at, without even taking too much of a look, is that the cosine rectangular and the damped AC results, they look pretty similar. They both show a lot of PD activity at two locations. What you don't see on the VLF sign, though, is anywhere near as much activity on either of the locations. So in this case, the VLF sign, it found the splice at 750 meters, only at the higher voltages, only above rated voltage, and only on C phase. And it found the problem splice at 900 meters, only at higher voltages, and only on A phase, where both damped AC and cosine rectangular found problems on all three phases, especially at voltages above rated voltage. So we'll take some time now to interpret the results. So what we see is that damped AC and cosine rectangular give similar results. The splices at 750 meters and 900 meters need to be repaired or replaced. Interesting to note that these are both the transition joints going from extruded cable into paper lead. And both of these showed some PD signals at or below rated voltage. I talked about this a little bit. The splice at 750 meters had problems on all three phases, up to 1,500 picocoulombs. And the splice at 900 meters showed all three phases up to 2,250 picocoulombs. With the cosine rectangular, very similar, except slightly higher numbers. And the splice, or the problem in the insulation at 1,000 meters, that was in some paper lead cable. So the VLF sign technology, though, gave us a false good reading. It showed the splice at 750 meters only on phase C, and it only had a value of 80 picocoulombs. Now, in this case, we had some very low background noise, but 80 picocoulombs is within the range of what would be background noise in typical field conditions. In my experience, background noise can go anywhere from 25 to about 125 picocoulombs for background noise. If the background was a little bit higher during this test, we wouldn't have been able to find this splice at all. And similarly, this splice at 900 meters with only 250 picocoulombs, that's still a very low signal. And it's important to note, too, that there was no PD measured at rated voltage. So keep in mind that slide I showed before. If the PD IV and EV are both above rated voltage, that's a completely different condition than if they're both below. So we got two very different results with the power frequency like results of damped AC and cosine rectangular compared to the sinusoidal. This table shows the inception voltage for all three phases, all three technologies, and for all three defects located. So with damped AC and cosine rectangular, especially the splice at 750 meters, we started seeing that problem almost immediately at half rated voltage. The problem at 900 meters took a little bit more, but we were still able to find that problem at a lower voltage than the VLF sine wave was. You can see that the VLF sine, the problem on C phase, only started at 1.1 times rated, and the problem at 900 meters only started at 1.4 times rated. So very different results, especially on this problem at 750 meters between sinusoidal and the other two waveforms. So the conclusion to this is certain types of defects are very sensitive to the voltage wave shape, specifically the slope at polarity reversal. In these cases, if the weak spots can be detected at all by VLF sine, they do require a much higher voltage, and they tend to give a much lower PD result back. So I'm going to ask you guys for some help here. Good data like this is very hard for us to come by. We're actively looking for customers to work with to develop more examples like this. And if you want to work with us on a project like this for publication, please contact us. I have my email address up there, and there's also an email address for the US Tech Support Group. Just note that in the email address, the group is spelled without the O and the U. So please contact us and help us with more examples like this. So here's some guidelines for what we can expect, some tolerances for PD level that we can see. And we can see that for XLPE and EPR, some extruded cable. On a new cable, the complete cable system, that's the insulation, the splices, and the terminations, should be PD-free up to 2 times rated voltage. That's very straightforward. We shouldn't be able to detect PD on a new system. On aged systems, though, we have a little bit more tolerance. In the insulation itself, it really can't tolerate PD, so if we find it at all, it's a problem. We're going to have to take some action. In joints and terminations, they can tolerate a little bit of partial discharge, so we're looking at levels 250 to 1,000 picocoulombs would be considered critical level, depending on the criticality of your cable and all. So, and these are, if we see this partial discharge at rated voltage, these are critical. Some guidelines then, if the cable is PD free up to 1.7 times voltage, we might be able to push our next recommended test off until maybe 10 years. If it's an important cable, you might want to do it more often than that, but cables that are PD free are generally in very good condition. The PDs between 1.3 and 1.7, maybe we do that every 3 to 5 years, depending on the criticality of the cable. And you can see that as the PD inception voltage gets lower and lower, our test frequency gets more and more frequent. These guidelines, they come from Megger's experience. There's no standards available for this. And through the experience of a utility in the Netherlands called Nuon. So we have a very similar chart here for paper lead cables. Obviously, this chart only shows aged paper lead because it's very, very rare to put new stuff in. But what we can see already is that the levels that are critical are much higher. We're looking at 20,000 picocoulombs in the insulation. Whereas if we think about extruded cables, if it was any partial discharge, it was critical. With paper lead, we can tolerate maybe up to 20,000 if it's scattered all over the place, or maybe up to 5,000 picocoulombs if it's in a particular point. Now think back to that case study. we found a problem in the insulation of the paper lead cable that was 500 picocoulombs. So that was 10 times less what our guidelines are here. So that's a condition that we can tolerate. And we can go through the chart here. If we find joints with up to 10,000 picocoulombs for an oil filled, or 7,500 for a resin type joint, and very similarly for terminations as well, that's where we would consider a critical level. And you can see, very similar to the extruded cables, as the partial discharge inception voltage gets lower and lower, our test time gets more and more frequent. So a little bit of a matrix here. You guys can take a look at this and think about how a particular cable applies to your system. But for instance, a cable that's very important, let's say it's feeding the airport or the hospital, and we find that it's in critical condition, that's the kind of thing that we want to change very quickly and certainly keep on top of with the diagnostics. If it's a little bit less critical, but it's still in bad shape, and maybe we can hold off a little bit on the replacement, but we still want to stay on top of the diagnostics. And you can go through this as you go through. A cable that's in very critical but is in good shape, maybe we only want to do diagnostics every 3 years. We want to make sure that it's not aging too quickly. But this is pretty common sense, pretty straightforward, but you guys can take a look. Another piece of information that we use for partial discharge is that mapping. So how do we determine this mapping? And that's a process we call localization. In this case, I have one particular partial discharge measured right here, and you can see it's got the arrow pointing at it, and the dot's slightly bigger. And what we can see here is the initial pulse and the reflected pulse, and I have a blue bar down here just to kind of highlight the distance there. I'm going to switch over to the next slide, and I'm going to pick a different point from the other weak spot. So now I'm looking at this point, but I keep this blue bar the same length. That's the exact same length as the previous slide. And you can see that my initial pulse and my reflected pulse are now considerably closer to each other than they were at the first example. So what's going on? How does this localization work? So when we have a partial discharge event in the cable, it induces a signal into the cable, and that signal travels in 2 directions. One of the signals travels directly back towards my receiver, towards my measuring equipment, and one of the signals heads towards the far end of the cable. Once this one reaches the far end of the cable, it hits the end and it bounces back, and it starts heading back towards the receiver. The receiver picks up this initial pulse, and that's when it starts the timer, and it starts sitting there and counting and waiting for this pulse to arrive. Once that pulse arrives, it stops the timer, and it can calculate a distance. It can calculate a time between the 2 pulses, and if we know the speed those pulses were traveling, we can calculate the distance. Of course, this example, I slowed it down so you guys can see. It doesn't really stop at the end. These signals don't stop. They flow smoothly through, but I slowed it down so you guys could follow along. What you might notice here is that our initial pulse and our reflected pulse, they look similar, but my reflected pulse is considerably shorter and a little bit wider than my initial pulse. And we call that effect cable attenuation and dispersion. Attenuation increases as the cable length increases, and it's as that pulse loses energy to losses in the cable system. It basically lowers the magnitude of the signal. And what happens is a marginal signal can then become unmeasurable. The other phenomena we have is called dispersion. Again, it's related to the length of the cable. As the cable length increases, the pulse gets wider and lower. Kind of similar to a TDR if you've used those. And that's because the cable filters out high frequencies. So we see here in this nice, sharp, tall pulse, it has a lot of high frequency components in it. And as that pulse travels down the line, it loses more and more of those high frequencies. So we no longer have that nice sharp edge, and we wind up with this lower and wider pulse. So for some further information, guys, we're going to be at the IEEE T&D conference in Denver coming up in April 2018. And Robert, who is our panelist here as well, he will be presenting a paper on this very similar topic. So make sure you stop by and see that. And we're also going to have a booth at the show, so make sure you come by and see us as well. Of course, Megger has the testing equipment for everything that we've talked about today. So we have here our VLF Sine 45 and also our 62. So we can now do VLF sinusoidal testing up to 45 or 62 kV. And these are suitable for PD or 10 delta diagnostics with sinusoidal waves or VLF withstand testing. We also have our TDS 40 and 60, which does testing up to 40 or 60 kV. And this unit has damped AC and cosine rectangular built in. It's suitable for PD diagnostics and VLF withstand testing. We have a unit called the TDM 4540, which combines the best of both of these. So we have damped AC, cosine rectangular, and sinusoidal all in one unit. This tests up to 45 kV peak, and this is suitable for all testing, PD, 10 delta, VLF withstand testing, and it is modular, or you can add on to it. You can start with the base unit and add parts to it as needed. We have our integrated test bands like our Centrix 2.0 and our Centrix City. These take our cable testing and fault locating and combine it into one integrated solution. Has a lot of safety interlocks. It's highly customizable unit. And finally, we have our DAC 30. This is up to 30 kV peak. It's damped AC only, which makes it ideal for PD diagnostics. What is unique about this one is it's completely enclosed. There's no external coupler with this, like you see on these other units. Everything you need is inside this case, and it's very small and lightweight too. So make sure you contact us if there's anything you want some more information on. Ask for a demo, ask for a quote on anything you see here. There is a box in the survey after the webinar if you want us to contact you, or you can contact us directly via your local sales engineer through our website or give us a call. So Jamie will go through some information about the survey here.
All right, thank you, Jason. At this time, the presentation portion of the webinar is officially concluded. And all right, we're going to go ahead and take about 30 minutes to answer as many of your questions as possible. Also, if you have any questions and you haven't submitted them already, you can go ahead and submit those now into the Q&A box, and we'll try to get to as many as possible. For those of you that are leaving now, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. On that survey, there's also a field where you can also request a demo or quote of any of our Megger products as well. A copy of the presentation along with a link to the video recording of the webinar will be emailed to everyone within the next 2 business days. And you can also view video recordings of previous webinars on our website at us.megger.com/webinars. And we don't have the new schedule for 2018 out yet, but it should be out here in the next couple of weeks, and that'll also be posted on our website in that same location. So be on the lookout for that. All right, now let's go ahead and get to some of your questions. Okay, first question is going to be for our panelist, Robert. You have spoken about PD mostly in reference to testing of cables and their accessories. Is there other applications for this technology, and is that more applicable for online type surveys?
Okay, hello everybody. So this is Robert speaking. What Jason presented on is mostly and specifically for offline cable testing, and then has to do with the special role that the cable has in the overall power system. The way it's used is it is the only distributed component. Most of the other components are localized and specifically located in substations. So this type of offline test is either an acceptance test mainly, is done partially type test in terms of type test in the factory. Now there's of course online and substation-specific PD monitoring. So it's a big difference between like offline diagnostics and PD monitoring. Megger has a few of these tools as well. This is mainly done by UHF and radio frequency measurements with devices that can be called handheld. They're not very, very large. And that is typically specific to substation equipment. So you can do PD analysis and to a certain extent PD localization, for instance, on switchgear, high voltage or medium voltage end terminations when it's coming into the substation. Transformers, like your high value assets, are typically targeted with online and in substation handheld applications. But again, this is a completely the apparatus is different, the principles are different, and for the cable testing specifically for the cable assets, you want to do offline testing because that's the only really suitable way of doing that. For instance, one major shortcoming also of online monitoring in terms of cables is that online monitoring or online PD is pretty much absolutely not suitable for longer cables, and most of the cables is also not accessible. That's another point. Then you have access to the cable in manholes at best. So yes, there is other technology available. We have some of these stuff in our portfolio as well, but that is for mainly substation application and substation apparatus assets.
Okay. All right. Thank you, Robert. Next question is for Jason. What is the minimum rated voltage where PD is a useful test?
Any rated voltage. The limitation I would say is that you have to make sure that the cable has a shield on it. So your very low voltage, your 480 volt cables, they're not mechanically constructed in a way that would, kind of be conducive to PD testing. But as long as the cable has a shield on it, so your 5 kV rated cables and above, you should be able to do some PD testing on it. With the lower voltages, though, some of your signals tend to be smaller. So if you're in a very noisy environment, you may not be able to detect the emitted signals. But generally speaking, pretty much anything from with a shield on it, your 5 kVs and up, should be useful for doing PD testing on.
All right, thank you, Jason. Next question is for Robert. Does the PD test relay back the distance found, or was that predetermined? And then part 2 of the question, can you speak about attenuation of PD signal on corroded tape shields and what can be done to get an accurate result?
Okay, yeah, that references back to what Jason said initially. All of that stuff was explained in detail in that webinar before. So if you need more detailed information, take your time and watch that webinar as well. To answer that in short, the PD test is the only test in the diagnostics world, so to speak, that can localize defects. And the way this is done is based on TDR technology, or radar, if you want to call it like that. And with that comes all the strengths and all the weaknesses of typical radar technology. So that means, the localization is done, as Jason showed in some of these slides, pretty much with evaluating the reflections and the run times between the different pulses. So it is actually a true localization of the weak spots and the problems. Now, speaking of tape shield, this is actually a very interesting question, and unfortunately, the answer to that is there's not much you can do on tape shield. Tape shield, and this is also a big problem for the cable fault location. Tape shield, initially, there is not much difference between the typical concentric neutral and the tape shield construction, but over time, the tape shield tends to corrode, and it's corroding specifically in the layers of the shield that are overlapping. So you have some chemical processes going on there that will start the corrosion. And at one point, it's almost like that these layers are fully insulated. And then you have a situation that the pulse is propagating as if it is propagating through a coil. And then the cable acts like a very harsh filter on the signal. So the attenuation is very, very high. And the answer is you cannot do much about this because you cannot really change that condition. So what you're losing first is a lot of range on the system. Like typically these systems, for instance, the DAC systems, have a few to quite some miles in range, and that's what you lose first. But if you have a really high attenuation, the pulse just gets attenuated away, and then there's nothing that comes back. You can go to the other end, especially if the circuit in itself is longer, and try to do a multiple point analysis. But tape shields in general are difficult cables if they have corrosion on them. So there's no happy answer I can give you on that. So it's very problematic because of physics.
All right, thank you, Robert. Next question is for Jason. That is, for the test capacity on VLF, are you just talking about PD testing?
No, I'm not. It's testing cables in general. The cable is a big capacitor, so we have to be able to fill that capacitor up and discharge it in the time that we have per cycle. So VLF withstand testing especially does suffer from this maximum capacity of the cable as well. So when we talk about the cosine rectangular, the damped AC, we have a much higher testable capacity, even on just the basic withstand testing. The damped AC has an even higher, so I guess the order of them is VLF sine tends to have the lowest testable capacity. Cosine rectangular is much higher, and damped AC is even higher than that typically. But it does depend on the size of the power supplies and all involved in each particular unit. But no, all of the cable testing technologies have a limit to the amount of cable you can test.
And just, this is Robert, and just to add to this, keep in mind that the main reason why the VLF technology was invented was because the DC high pod was not available anymore. So this is a tool to replace your standard commissioning test and maintenance test withstand. And the cosine rectangular has naturally a much higher test capacitance than a sinusoidal test set because of the physics involved. Now with the DAC is mainly a PD diagnostics waveform. And just to make this clear, this is not something that is new overall in terms of technology. DAC was the first diagnostics technology that was qualified internationally to give you 50, 60 hertz comparable results. And there's pretty much no discussion in the industry or no dispute that this is not the case. And originally, this technology has evolved to do from the transmission type cables, from the high voltage cables, and is now migrated down into the medium voltage level. And it is a very proven technology that is in use internationally for well over 10 years now. And IEC 6270 is the governing standard for that. And all those waveforms are standardized and discussed in that standard as well. So DAC is your go-to diagnostics wave shape, while the cosine rectangular is your go-to withstand wave shape. And now what Jason also explained very nicely was that in IEEE 400, you have this combination test that is called a monitored withstand. And to make this clear, this is a fully standard compliant VLF test, as you have to do it anyhow, but you use the partial discharge as a trend indicator. So the way you do the test is much different than from a pure diagnostics test, as Jason explained, with these different steps where you try to determine the different parameters, specifically the inception voltage. You apply the voltage according to the withstand table, table 3 in IEEE 400.2, but you use the PD as a trending indicator to see if there is any condition going on. And initially, just to give you a little bit more historic background on that as well, cosine rectangular, like SIBA KMT, never initially intended this to be used for PD. Like, it was the first VLF waveform that was invented, made commercially available in 1983. And customers approached us to ask, hey, can we do the PD test with cosine rectangular as well? And to be very honest, we said, well, like, let's see. And then qualification studies were made where then it was shown that the CR technology is giving you, like DAC, power frequency comparable results. And this is how this involves. So for a commissioning test, when you want to combine all of that CR and then the DAC, and the DAC is, like, as I said, just the diagnostics, and its high test capacitance comes from the fact that you're just releasing one shot and you take your time of charging the cable. It is not a continuous waveform. So you have sometimes on transmission cables, you charge the cable over 5-10 minutes sometimes, and then you release the shot. And of course, if you can take that time with a non-continuous waveform, you get a huge test capacitance out of that. Just to clarify this.
Okay. Thank you, Robert. Okay, next question is for Jason. Regarding slide 39 and 40, what are the tolerable PD values for aged cables?
Let me go back to slide 39 and 40. Yes. So, yeah, they're here, but the basic idea of this is that for extruded cables, XLPE and EPR, it should be PD free up to twice rated voltage. There should be no detectable PD. That criteria isn't really practical for age cables. You know, you're going to eventually have some PD, but the criteria then for age cables on extruded cables is for the insulation itself. Not splice, not termination, but the actual insulation, that should be very much PD free at rated voltage. For joints and terminations, there's a lot more material there, so they're able to tolerate a little bit more partial discharge before they actually fail. But just as a guideline, like, again, I can't stress enough, these are not standards, they're just some guidelines that we can give you. Joints and terminations, we're looking at 250 to 1,000 picocoulombs before we're considering it a critical. But like, if you detect any PD in an extruded cable, that should be a red flag, and you should be, at the very least, closely monitoring it. When we talk about paper lead cables, these guidelines are only for aged cables. I don't present anything for new cables because nobody's really putting in new lead cables. There's maybe a few exceptions here and there, but generally speaking, it's any lead cables that are out there are aged. You have to consider that the insulation material is constructed completely different. Extruded cables are a single extrusion. They're rubber cables. Where for a paper lead cable, you have these wraps of paper, upwards of 100 wraps of paper around. It actually takes a little bit of effort for the partial discharge to jump these layers. So it has to jump hundreds of layers, and each one of those takes some effort. So you can have some very high PD values with a cable that's actually pretty reliable. So we wind up with partial discharge values that are in the thousands of picocoulombs anywhere on a paper lead system. Anything that's kind of concentrated in the range of 5,000 picocoulombs, that's certainly going to cause some alarm bells. It's kind of a minimum number. But yeah, if I start seeing upwards of 2,000, 3,000 picocoulombs on a lead cable, I might start taking some closer looks at it. So I hope that answers your question. Do you have any comments?
Yeah, just real quick to add to this, just keep in mind, as I said, this is, or as Jason said, sorry, this is experience values that we, collected and put together for over 20 years now, and working with utilities, and mainly these experiences are coming from Europe. And now you have to remember, Europe is ahead in terms of the cable infrastructure compared to North America by quite some time, and also the regulations are much stricter. So they are not allowed by any means to put in new oil cable, and they're like very progressive with like getting the oil out of the system. And now pretty much all of their infrastructure is aged. And on top of that, what you typically see on those cables is that pretty much all of them, with some exceptions, but you can say with little inaccuracy, that all of them show PD anyhow, and their extinction voltage at operating voltage, and their extinction voltage it's much less. So people over there in terms of lead are not even concerned about the extinction voltage because they have PD anyhow. So this is how these numbers are collected: experience values, utilities, and yeah, related to the infrastructure as it is there in Europe.
That's a good question.
So, do you have another one?
Yep.
All right, thank you guys. Next question is for Jason. Here, VLF sine wave test is not showing PD, but it is showing in other waveforms like CR and DAC. How do you cope with this? Also, are background noises too sensitive to detect PD emission?
That's a very good question, and ultimately that is the whole point of this webinar, is to kind of illustrate the point that if you're only using VLF sine technology for partial discharge testing, you may miss partial discharges, and you would never know. There's no way for you to know that if you're only using VLF sine. So how do you cope with it? You cope with it by using a different technology. You use damped AC or cosine rectangular. You use something that's closer to power frequency. Before I answer the second part of that question, would you like to add to that, Robert?
How do you cope with this? Well, just to summarize what Jason said, is pretty much there's defects, there's no question with this, where all the three waveforms are the same. But then there's defects where they are quite different. And with these case studies, and Jason presented one case study here in the paper I will be presenting in IEEE. I managed to put in 3 in those 5 pages, but we have a few more. And what you can pretty much say is that on average, I repeat, on average, that sinusoidal VLF, when used for PD testing, does not give you comparable results to other waveforms that are in the so-called power frequency range, 20 or 30 hertz to 500 on average. There's defects where it's the same, but there's defects where it's not the same, and you as a user, as Jason said absolutely correctly, you'll never know, and you do not know when you cope with, when you deal with one situation versus the other situation.
Okay. So what was the second part is, are background noises too sensitive to detect PD emission? Not quite sure, but I'll mention about background noise. There's nothing you can do about background noise. You just have to measure it and live with it. And if you're in too noisy of an area, you may not be able to really do effective testing. But like I said, my experience with background noise, it can be as low as maybe 20 picocoulombs is about the lowest I've ever seen. Up to about 150 is about the threshold where we can do meaningful testing. And what that means is that if there's any partial discharges, at or below the background noise level, I can't detect them. So for example, like that VLF sine that we saw of 80 picocoulombs, that was in a very, very clean environment that they were testing, and the background noise was very low to even be able to detect that. If you're in a more common area where a 50, 60 picocoulomb background noise, I wouldn't even be able to detect that, that signature from the VLF sine. So having these technologies that give you a higher picocoulomb value for your testing, it is beneficial. It's the same defect. We're not making the defect any worse or better, as it were. We're just making it easier for us to detect it. So yeah, the background noise is what it is. It's a field environment. There's nothing we can do. We just have to measure it and live with it, and it does have some bearing on the test. And if the background noise gets too much, we can't do meaningful testing anymore.
Yeah, just one more word. Keep in mind that what Jason spoke about and what you also saw on the test results and what experience tells from Europe since the early 2000s, these defects that you are after with PD diagnostics are generally in the hundreds of picocoulomb. Defects in accessories, localized, like isolated weak spots, as the technical term is, like you have the shield got extruded into the main insulation, there's semicon tape missing, whatever, manufacturing defects, which are, to be honest, very, very, very rare. The quality, specifically also from the manufacturers in Europe, is like excellent. You will barely find these things anymore, but if you find them, these isolated weak spots, they are generating PD in the hundreds of picocoulomb. So with this, the background now is typically, if you're not really like in the craziest thinkable environment where you have like hundreds of picocoulomb background noise, you will detect these weak spots because of their activity. So what's the next question? Thank you. Yeah.
Okay. All right, thank you. Next question is for Robert. Do you have any PD, or does Megger have any PD test equipment to test 72 kV rated power cables? Part two is, do you also have any equipment for VLF testing of high voltage cables?
Okay, so yes, we have equipment like that. We have, just to clarify this, we have DAC technology for the medium voltage cables, and then there is DAC technology for the high voltage transmission cables. These systems are called DAC 200 and DAC 300, according to their output, 200 and 300 kV. And we're using them quite frequently in Europe and other parts of the world on transmission cables. So that's for the DAC part. Now, VLF test equipment for high voltage. Now, here's a little bit of a pitfall. IEC, which governs pretty much the entire world except North America, like the US and Canada, does not recognize VLF as a testing technology above 36 kV rated cables. So anything that is sub-transmission, like in the US terminology, sub-transmission, transmission, ultra-high voltage transmission, or whatever, it is not done with VLF technology in the rest of the world. It is done with something that is called series resonance test sets. This is, by the way, the technology that came out the first for the transmission cables and defined this, what's called the power frequency range, 20 to 500 hertz. So for those higher rated cables, we have, for the VLF withstand, we have some VLF test sets that can go up to 80 kV output, but since our factories are located in Germany and all that technology came out of there, it leans towards IEC practices. So at a certain point, we do not have VLF test sets that go that high for that matter of fact. I hope that answers the question.
So just to summary, we have damped AC technology up to 300 kV, and we have cosine rectangular technology up to 80 kV.
All right, thank you guys. Next question is for Jason. If cable length is less than 200 meters, can we measure it using DAC?
Yes, but you'll probably need a support capacitor. On my diagram wherever that was in the presentation, you need a certain minimum amount of capacitance in the system, whether that comes from the cable or a support capacitor, it's all the same, but you need a certain minimum amount of capacitance. And yes, cables less than 200 meters can be tested, depending on the equipment. Some of the equipment has the support capacitor built in, some of it doesn't, but you may need that. So.
All right, thank you, Jason. Here's another one for you, Jason. You also said online PD testing for live working system utilities don't allow to apply more than the rated voltage. Then in this case, how will you detect PD?
So I was being serious, but being a little bit joking about it. You can't call up the system operator and ask them to raise the voltage for you for your online PD testing. So how do you determine the inception voltage? How do you determine, assuming that PD is not present already at working at operating voltage? How do you raise the voltage up to determine what your inception voltage is? You can't. It can't be done, because to raise the voltage up for your test cable, you'd have to raise the voltage for the entire system. So to answer your question, I think you hit the nail on the head, is you can't do what you're asking to do. That's why the offline technology is very nice. It solves a lot of these problems. We bring our own power supply, so we have control over it. We can isolate that cable, apply whatever voltage we choose, and find out the inception and extinction voltage, which, as you saw in this presentation, makes a big difference in the type of corrective action we might choose to take. So, very good question. I think you hit the nail on the head with that, is we can't do this type of testing with online technologies.
All right, thank you, Jason. Next question is for Robert. What was done with the tested cables that showed poorly on 2 out of 3 tests? Are they still in service?
Okay, so to give you a little bit of the aftermath after that test, what Jason showed you, by the way, was done at a German utility company that serves around 500,000 customers. So it's not huge, but it's also not small. And what was done was that these splices were opened up and problems were found and addressed, so to speak. So there was some repair work done. The PD activity that Jason showed you with the cosine rectangular in the cable insulation, that was in lead cable, like PILT cable, or let's say the European equivalent. It's called MIND, MIND. It's mass impregnated non-draining. It's very, very, very similar to PILT. And because it was not very high in magnitude and in PILT and not very concentrated, it was pretty much left alone, so nobody opened the cable at that spot. But what was done, and what Jason showed in this very nice slide with the risk assessment, keep in mind, the technology, it is not a crystal ball. Doing this test, you cannot walk away from the test and say, okay, that cable is failing in 6 months, 24 days, 38 hours, and so forth. You cannot give a horizon. We're not there yet, and it is very difficult to make these evaluations. There's still scientific work being done to classify that more. However, what you do is you try to gain scientific data for the risk assessment, and what these people were doing after fixing those splices, or at least like improving the quality. And they are monitoring those cables now a little bit more often than before to see if that spot develops into a more severe spot. So that was pretty much it. So there was action taken after that, because it was unclear if those PD activity was on the oil side, on the wet side of the transitional splice, or on the dry side. And they found some tracking and respliced, repaired, and then the PD activity in the cable is just a little bit more closely monitored, but it's not really a reason for concern. Again, in PILT, very low magnitude, not too crowded, not in one spot, and so that was pretty much the outcome of that.
All right, thank you, Robert. Next question is for Jason. Why can't you fine-tune the DAC to have 60 hertz frequency or very close?
The technical reason is inside the equipment there's a fixed inductor. So to get to exactly 60 hertz, you'd have to match the inductor and the capacitance of the cable exactly. And that's not really practical to have a tunable inductor to match every cable. So we just take an inductor that's, you know, suitable for a range, and the frequency then depends on the length of the cable. So to get exactly 60 hertz frequency out of a damped AC, you need a pretty long cable, something, you know, nearer the longer lengths that this is capable of testing. As the cable gets longer, the frequency of oscillation gets slower. So when we say that 500 hertz, that would be on your very short cables, something like, yeah, those 200-meter cables without the support capacitor might be oscillating in the range of 500 hertz. But something, you know, a couple of kilometers long, you know, without, you know, it might be in the range of 60 hertz or something. So the real reason is there's a fixed inductor in the equipment. It's not tunable for the system, which is what you would need to get to exactly 60 hertz.
All right, thank you, Jason. I have another one for you. Is there any difference in VLF testing using a sine wave, square wave, or triangular wave?
Yes. The short answer is yes. Let's discount sine wave for the time being and talk about the other two, square wave and triangular wave. As the cable capacitance gets larger and larger, if you apply a square wave, it will get closer and closer to a triangular wave, just because the long cables filter out the high frequencies, and those sharp edges on the square wave will get slower and slower. So eventually, they'll become the same wave. The other problem with square waves and eventually triangular waves are you tend to have overshoot at the voltages. So your RMS voltage might be, pick a number, 10 kV, but your actual peak voltage could be considerably higher than that because of the overshoot, because of that fast transition time. So if you think about our cosine rectangular from a zoomed out view, that does look a lot like a square wave from a very zoomed out view, but it's really very clever. The cosine rectangular doesn't overshoot because we have the inductor and all in there. It's a sinusoidal wave for half a cycle, basically. So it might look like a square wave, but it very much is not. Is there any difference in VLF testing using a sine wave? VLF sine is a perfectly acceptable wave to do withstand testing that's recognized by IEEE, as well as cosine rectangular too. So sine wave is a perfectly fine wave to do withstand testing.
Yeah, just a little comment to that. Yeah, square wave, just to make this clear one more time, square wave is not the same as cosine rectangular, and a triangular wave, for instance, is not recognized by any test standard as well. There were some experiments with this, but it never got anywhere. So a triangular wave VLF is not supported by any standard anyhow. And the only real application for like square waves, because I know there are some testers out there, and typically the equipment gives you the option because, you know, it's there, you know, you offer it because you can. That this is done by switching, and you have these transients, and it does not look smooth like the cosine rectangular because that's a resonance, so you have no harmonics and all of these the physical effects. And the square wave, the only real application that we have in the field is when you want to do a very quick proof test, like you used to do with the DC high pot, but you don't want to use the DC high pot, then that's okay if you want to apply a voltage like for a very, very short amount of time. But as Jason correctly said, the sine wave is the internationally standardized waveform, as it is the cosine rectangular, because that came first. And the square wave and specifically the triangular wave are not really common. There's no equipment really commercially available, and it's not supported by standards. So it's sine or cosine rectangular, and then keep in mind in what world you're operating, IEEE and IEC, and there's different test values in those two worlds, and just apply the voltages accordingly.
All right, thank you, Robert. Next question is for Robert. Is the TD SNT 40 and 60 series only available in the range of 30 to 500 hertz?
Well, this question is kind of backwards a little bit. The TD-SNT series was the first combination test set on the market. It combines cosine rectangular VLF with a damped AC diagnostics part. And as Jason explained, the reason for that is because the two technologies in terms of circuitry are brothers. Like you modify the cosine rectangular wave circuit a little bit, and you get a DAC waveform out of that. So that was a natural thing to combine. And since the DAC technology is governed like internationally by IEC 60270, and this power frequency range, as the technical term is, which is this band, which came from the continuous resonance test sets for the high voltage cables. The TDS follows this requirement. So that is the frequency that you can apply with the DAC. So the DAC portion of the TDS fully complies in any aspect, calibration, measuring, application of the voltage and everything with the IEC standard, and the 0.1 hertz VLF portion. So when you just do the withstand, complies with the VDE, the Senelec, the IEC, and the IEEE 400.2, also with all the international standards as well. Okay.
Thank you, Robert. Next question is for Jason. By noise, do you mean in the audio domain or high frequency noises?
No, very much not audio noise. By noise, I mean signals in the range that partial discharge would be present, which is some hundreds of megahertz. Corona is very similar to partial discharge. So if you're in a switch yard and there's some corona going on, that can induce signals into your test equipment, things like that. Something like a switching power supply in a computer might have enough high frequency components in there to affect you. Things like that. Some high frequency, some hundreds of megahertz type of signals that are inducing these signals into your test equipment. But talking or something like that is not going to affect your readings. A radio that's passively listening, like an FM radio, that's not going to affect anything. Just passively listening. A walkie-talkie certainly would. If you're using radios to talk to each other, that could affect your signals as well. But something like fluorescent light bulbs too can they switch in that type of frequency as well. So high frequency radio interference type noises.
Yeah, just to add to that, just to explain that the IEC standard is very strict and very detailed in terms of the measurement circuit that you're using and how these signals are processed and how the signals have to be integrated. So the range, pretty much like partial discharge, these signals, they can occur over a very wide frequency band that stretches from some lower kilohertz to, as Jason said, to the megahertz. So for instance, 150, a few hundred kilohertz, and then up into the megahertz is this partial discharge frequency band. And when you do it online or with handheld in the substation for switchgear and so forth, you typically have the choice between several different sensors that feeding into the system. So you have UHF, and then you have also radio frequency antennas for certain applications. When you do your frequency sweep there to find sources, you're doing this in the different bands. And for offline testing, you pretty much integrate the whole signal from the low kilohertz to the high megahertz, and that gives you the full charge that you're, like the apparent charge that you are actually getting. And of course, if there is an interference in these frequency bands, then you will see this. But for sure, not like let's say, audio frequencies like our ear or whatever, that's typically too low.
All right. Looks like we have time for one more question. This one is also for Robert. Do you have any experience with respect to PD testing on high voltage 72 kV or 240 kV fluid-filled pipe type cable systems?
I have to say not so much in the US market, but in Europe, we're at the moment pretty busy with our DAC 200 and DAC 300 technology for the utilities to use that technology for the diagnostics on those high voltage transmission type cables. We have a few case studies, and we have a few, let's say, samples that we sometimes show in the presentations when we address the high voltage transmission type cables, which we typically do separately because it's kind of by itself. But yeah, we have some experience there. If you really want, like, we could put you in contact with some of the mega guys, the SIBA KMT guys in Europe, and they could discuss that with you and make some information available to you if you are interested. Just send me an email or the technical support group or Jason, and we can talk. Okay?
All right. Thank you, Robert and Jason. Looks like that is all we have time for today. We apologize if we didn't get to your questions or get all of them answered. There was a few I don't think we were able to get to, but we will follow up with you offline in the next couple of weeks and get all those, make sure all those are answered. I just want to thank you all again for attending. If you can please remember to answer the survey, we'd really appreciate it. That's it. Thank you all again, and have a happy holidays.
Yeah, happy
holidays, everyone.
See you guys.